Good morning. First of all, happy birthday, Shankar. It's great to be back. Actually, I came in a little bit early yesterday, and first thing I did is went to Nefeli. But it was a little bit late for everyone to be there. It was around 7 o'clock. Didn't find anyone, but great to see everybody here. You guys all look just the same. And so I was here, a PhD student with Shankar and the whole team here. After graduating, I actually spent 4 more years at Berkeley, working on the automated highway system project at PATH. And that gave me a distinct opportunity to work with a lot more of you than what I would have done otherwise. So that was a great time at Berkeley. And then after Berkeley, I joined Honeywell. At that time was a controls company, and our, really our focus was that Honeywell allows you, the customer, to control your environment, whether it is your comfort in your home, or whether it is a modern process control industry, control room, which is controlling most of the refineries and chemical plants, or it's airplanes. So that was the focus, and it was a great opportunity to take the learnings from Berkeley and see what can be productized. What can we take and make it into a day-to-day, really simple, becomes the fabric of life, right? And then that doesn't remain an R&D topic anymore. So that is where I will give you a little bit of glimpse of a case study from an urban infrastructure perspective. I've picked the aerospace as an example, and as you see, most of the urbanization in the world is happening in developing nations, China, India, Southeast Asia, Latin America, and you can see the amount of airport construction happening there. It's just incredible. So what we need is that urban infrastructure, the airport infrastructure, where you can get that most effective air travel in and out of the airport. And I believe Hamza would probably follow through a little bit later. And hopefully the problems I pose, if she has an answer, then we're done. Right? So let me give you a little bit of a history. Right? When I joined Honeywell, we had all these different opportunities to take controls into different parts of an airplane. Right, all the way from engine controls, APU control, the cabin pressurization, all the environmental control system. I mean, this is something we don't really recognize, but all of these things Honeywell touches, and all of these things are opportunities to add controls in there. And at that time, fly-by-wire was like a novelty in real life, right? Airbus 320 and 777 were just coming in. John can tell a lot more about fly-by-wire than I can. But what our team did is, take it down to the masses. So today, most of the airlines, all 3 major airlines in US, they fly Embraer 175, 195 series for regional transport. That's the smoothest ride you will ever get, I guarantee it, because that's designed by us with Embraer. And also 787 now. That's pretty good too. So what has happened is fly-by-wire system, it took a long time to get adopted by everyone, and partly because that takes away the linkage from human pilot to the actuators, takes that away completely. Earlier it was mechanical, and now it is computers. So your actuation signals by the pilot, as well as all the sensors that are coming in, where the airplane is, where it is going, how fast, and proximity to terrain and weather and all that, that's all taken into a computer. And then that computer decides what signal to send to the actuators. So in addition to the controls analysis, you also need to have something here that how do you implement it? That redundancy management, multiple redundant computers, that's the brain of the system, multiple redundant communication networks that go from that avionics bay computer into the actuators, and then multiple redundant actuators. And then you have to convince the FAAs of the world that this is safe. Okay, that's what takes a long, long, long time. So after we do all this, and it's become like commonplace now, autopilot obviously has been there before. Autopilot simply gives you a little bit of automation of the cockpit tasks, but fly-by-wire system actually gives you the safety. And then we had also good position in flight management system that gives you end-to-end trajectory optimization, so you can fly optimal trajectory from fuel and time perspective from A to B. So we are done with all this. Can we declare victory? That controls has delivered its promise, safety and efficiency. Well, the answer will be yes if there was only one airplane in the sky, right? But now when the pilot comes close to an airport, you get vectored. You get vectored around, and all the benefits of flight management system that you get in terms of fuel savings, slowly you start losing it, especially when you get these descents that are, step descents, not a continuous descent. That just takes away all that benefit. One more thing happens though, that at some point the pilot starts thinking, I'm getting vectored, I'm getting all these commands, so let me take over. So imagine circa somewhere early 90s, American Airlines 757 flying into Cali, Colombia, and the pilot lost the context. The pilots lost the context. It was flying FMS. And they punched in a new waypoint. This airplane is coming into land. They had already passed that waypoint, but they punched it in again. The airplane starts going back to the waypoint. It's coming in through a valley, right? I mean, look at these instruments. This is what I flew in yesterday, by the way, from Minneapolis to here. We're still flying these things. This is 757 cockpit. Each and every sensor that you saw in the previous page has a separate display. Pilot is supposed to integrate it all in their brains and get that situation awareness. So when you hand over from control, automatic control to pilot control, you need to transfer all that context into the pilot's brain. This situation will happen more and more when we go to autonomous driving cars, that all the automakers and Google and Tesla and everybody is designing. How are we going to solve that problem? So what we did at Honeywell and many others in the industry is that we went from this cockpit to this cockpit. This is one single integrated cockpit that tells you everything you need to know on one display. And the air transport folks are a little bit further behind on adopting this, but the business jets of the world, Gulfstream, Dassault, Bombardier, they have already adopted it. It's been in the marketplace for about 5 years now, and it's very successful. So I'll show you a small video, like a two-minute video, to show how what's the benefit of that. And this is where controls itself is not the only thing that you need, but you need cognitive science, the combination of control and cognitive science. So
the Honeywell Synthetic Vision System, or SVS, installed in the Gulfstream Plainview cockpit, greatly enhances a pilot's situational awareness. In addition to providing standard flight and navigation data, SVS provides a three-dimensional view of surrounding terrain, obstacles, and runways. Using the entire primary flight display, SVS presents the pilot with images of the external scene topography. This is done by using existing aircraft terrain databases from the Enhanced Ground Proximity Warning System, or EGPWS, combined with position data from the aircraft navigation sensors. This data is oriented in real time with aircraft attitude and altitude. Runways in SVS 2.0 are displayed with additional enhanced features such as runway numbers and centerline markings. In addition, runway surfaces are displayed with added texture so that motion is more apparent. In SVS 2.0, the arrival runway selected in the FMS is displayed with a runway lead-in line and distance markers. The distance markers are placed at 1 mile intervals and are a supplemental tool that can be used to assist in maintaining situational awareness and a stabilized approach. The enhanced HSI presents a top-down view of terrain similar to that shown on the map display. EGPWS alerts are displayed on the enhanced HSI as they are on the standard 2/3 HSI. The terrain colors and highlighting match those used on EGPWS terrain alerts on the map display. Intruding aircraft are displayed on the HSI during a TCAS alert. The symbology is the same as a normal TCAS display.
So problem solved, right? Now we got control handover to pilot is done correctly, and the pilot is in the loop, everything is good. Well, now we go to a very busy airport, like here is an example of a Dubai airport. This is the airport with the highest international traffic, 78 million passengers, and only 2 runways which are actually quite close to each other, so they could only use 1.5. And so can anyone tell me what is the most dangerous part of your flight? It's on the ground. It's on the ground. So, and especially all the landings and all that, people have landed on the wrong runways. They have landed on taxiways. They have taken off on taxiways. They have landed short, like there was a Korean Airways flight at San Francisco, landed short. They have landed long and run out of runways, all kinds of things. So, and then when you land from there to go to the gate, I mean, this is what you have to.
1 Roger, taxi straight on Zulu, hold the beam, Foxtrot 20.
Straight on Zulu, a beam, Foxtrot 20 to hold, Emirates 841.
Lima 73, change of plan, you have to go on Kilo and then Lima 4, hold short of Mike.
Kilo, Lima 4, hold short of Emirates 73.
You have to pick out your call sign and you have to remember all of that. And then go to your place, you know, at night when you don't have
ground up to mobile 109, only
familiarity with the airport. So where we are going with that is yet another system. Dubai Airport is the first pioneer, and Honeywell just deployed that earlier this year. Can we shut down the lights, please? Can we shut down the lights a little bit? So this is a simulation, but this system is actually actively working. This is landing at Dubai Airport on the simulator. But if you are flying Emirates, Emirates gives you the view from the front camera, so you can actually watch this. You can watch this happen in real time on any seat. So there's nothing magical here, you just land. So once you get off the runway, you will see what happens. I have turned off the noise deliberately because you don't need to listen to any noise. So this is called follow the greens. And you can see if you are going to take off, get out of the active runway from here, the next few hundred meters are green, and then everything else is dark. As you get off, the next thing becomes green. As a pilot, you just follow the green. You don't have to remember, go to Kilo 9, wait, go to Lima 5. This one keeps going. So now what we're doing is, we are...
Is that synthetic or is that actually on the ground?
This is actually on the ground. 39,000 lights, each of it can be individually controlled and monitored. And each of it can turn into green, or there are also red lights that you will see cross signs that you will get stop. And we are trying to provide this guidance to each and every vehicle on the ground, which are, in addition to the airplanes, all the baggage handlers and fuel trucks and everything like that. But now the issue is that you need to convince the regulators that our dynamic optimization problem that we're trying to solve is safe for all these. So here you can see the, there is a red light that just says stop, don't cross this active runway, and then you get it started. So just moving on. In order to do that, one quick last minute, in order to do that, what we need is we need to now transform the controller in the control tower. The controller in control tower looks just like that 757 display, right? 4 different displays for 5 different displays for 5 different things, 5 mice and 5 keyboards, and you're trying to get, like less than 1 minute, between landings and takeoff. I mean, this is amazing, right? How they work. So what we're doing is combining 12 different systems into one single display. And you can get from pushback to takeoff, or from there to there. For every aircraft, these are calculated in real time, and we are monitoring 350 loop sensors plus all the radar vigilance that's going on, and controlling 35,000 lights to solve this problem continuously and give you that optimal solution. This is 4D trajectory on the ground. What we're still missing is that 4D trajectory end to end once you take off to land. I mean, that's a much harder problem. Even this is not very easy, but you have to find a progressive airport to do it first and then go with the rest. So now we need controls, cognitive and computer science. And it's just an example of how Honeywell has changed itself. We were a traditional industrial company, and this is a chart came from our strategy meeting just last month. We are trying to become a cyber industrial company. So it's very appropriate to come here and talk about it at a cyber physical system workshop. The whole company is trying to become cyber industrial and solve societal problems like intelligent transportation, energy efficiency, smart grid, and so on. So I look forward to all the great discussions throughout the day, and hopefully I can take something back and we can productize it and bring all that benefit to whole society. So thank you very much.